A spacecraft the size of a school bus tore itself apart inside Saturn's atmosphere at 111,000 kilometers per hour, and in its final 91 seconds, it sent back a set of readings that scientists still cannot fully explain. Welcome back to Infinity Alert, where we go beyond the headlines and into the real science behind the universe's biggest mysteries. On September 15, 2017, NASA's Cassini spacecraft deliberately plunged into Saturn's atmosphere, ending a 13-year mission that had rewritten what we knew about the ringed planet. This was not an accident, and it was not a failure. It was a planned death, designed to protect Saturn's moons from contamination. But in its very last moments, as the spacecraft burned apart, its instruments recorded data that directly contradicted models scientists had spent 30 years building. A senior researcher on the mission would later describe the findings, in a peer-reviewed paper, as difficult to reconcile with any known process. That single sentence, coming from a scientist who had studied Saturn for decades, is the reason this story still matters today. Cassini's instruments were not malfunctioning. They were working perfectly, and what they measured simply did not match what physics predicted. This is not a story about aliens, hidden messages, or secret cover-ups. It is something far more interesting. A real, documented case of humanity's best models running straight into the wall of the unknown. And the strangest part is this: the story isn't over. New discoveries from Cassini's archived data are still being published today, years after the spacecraft ceased to exist. To understand why Cassini's final moments were so significant, you need to understand what scientists thought they already knew. Cassini arrived at Saturn in 2004 after a 7-year journey from Earth. Over 13 years, it completed nearly 300 orbits, flew past Titan more than 100 times, and returned hundreds of thousands of images. By any measure, it was one of the most successful planetary missions ever flown. Scientists believed they had a solid understanding of the Saturn system, its hexagonal polar storm, its intricate ring structure, and its icy moons. But there was one region no spacecraft had ever dared to enter: the narrow gap between the innermost ring and the top of Saturn's atmosphere. That gap is roughly 2,000 kilometers wide, vast by human standards, but tiny compared to Saturn itself. Engineers assumed it was filled with ring debris and dust, dangerous enough that a spacecraft flying through at orbital speed could be damaged or destroyed. For 13 years, Cassini stayed well clear of it. In its final months, a phase mission planners called the grand finale, controllers made the calculated decision to send Cassini through that gap, not once, but 22 times between April and September 2017. What the spacecraft found there upended assumptions built over 3 decades of research. The first surprise was simple but important. The gap was far cleaner than predicted. Models had forecast a region dense with debris, dangerous enough to justify using the spacecraft's own antenna as a shield during the first pass. Instead, the actual particle count came back dramatically lower than expected. Something was keeping that region far emptier than the models allowed. And to this day, no single explanation has been confirmed. Some researchers point to Saturn's magnetic field, sweeping charged particles away. Others believe there are dynamics in the ring system itself that are not yet understood. Either way, a 3-decade-old model of how planetary rings interact with their parent planet's atmosphere had to be reconsidered. The second surprise was far stranger. As Cassini repeatedly dove through the gap, its onboard mass spectrometer, an instrument built to identify the chemical makeup of anything it encountered, began detecting complex organic molecules. Not simple gases like methane, but larger, more structurally complex compounds. The problem is that molecules like these typically require very specific conditions to form: stable temperatures, sufficient pressure, and long periods of time undisturbed by radiation. The gap between Saturn's rings and its atmosphere offers almost none of that. It is bitterly cold, close to a vacuum, and bathed in intense radiation from Saturn's own magnetic field, an environment that should destroy complex molecules, not build them. And yet, there they were. Scientists involved in the mission described what the spacecraft found as a genuine chemical cocktail. Water, yes, but also organic compounds and fine silicate particles all flowing from the rings into Saturn's atmosphere in a process researchers call ring rain. The term existed before Cassini based on indirect evidence, but the grand finale data showed that this material rain is heavier, more chemically complex, and more variable than any previous model had predicted. Then came the third and most fundamental surprise, one with implications that reach far beyond Saturn's rings and into the basic physics of how planets generate magnetic fields at all. Every planet with a strong magnetic field, Earth, Jupiter, Saturn, Uranus, and Neptune, generates that field through the motion of electrically conducting material deep in its interior. On Earth, that's molten iron churning in the outer core. On the gas giants, it's hydrogen compressed under such extreme pressure that it behaves like a metal. A fundamental prediction of this process is that a planet's magnetic axis should be noticeably tilted relative to its rotation axis. Earth's magnetic poles sit roughly 11 degrees off from its geographic poles. Jupiter's tilt is about 10 degrees. Uranus and Neptune are tilted more than 50 degrees. Saturn is different, dramatically different. Before Cassini's final orbits, scientists already knew Saturn's magnetic field was unusually well aligned with its rotation axis, within about 1 degree. That alone was puzzling. But Cassini's grand finale measurements, taken as the spacecraft repeatedly passed through the strongest part of Saturn's magnetic field, produced by far the most precise measurement ever made, and the result was almost unbelievable. The tilt was measured at less than 0.0095 degrees, not even a hundredth of a degree. This matters because of a well-established principle in physics called Cowling's theorem, which states that a perfectly symmetrical magnetic field cannot be sustained by the fluid motion that generates planetary magnetism. Something has to break that symmetry, even slightly. Saturn's field appears to defy that expectation almost entirely. Researchers on the mission have openly stated that this finding poses a fundamental challenge to existing models of how planets generate magnetic fields, models that have worked for every other planet we've studied. Multiple explanations have been proposed, from hidden conducting layers deep inside Saturn to unusual patterns of internal rotation, but none has been confirmed. As of 2026, the question of why Saturn's magnetic field is so precisely aligned remains one of the genuinely open problems in planetary science. But the most extraordinary Cassini discovery didn't come from Saturn's final orbits at all. It came from a small, icy moon, and a mystery that wasn't fully solved until 6 years after the spacecraft was gone. Enceladus, one of Saturn's smaller moons, is covered in bright, fresh ice. In 2005, Cassini discovered something remarkable at its south pole: long parallel fractures nicknamed tiger stripes, from which enormous plumes of water vapor and ice erupt continuously into space. This meant Enceladus had an internal heat source, driven by the gravitational tug-of-war between the Moon, Saturn, and neighboring moons. Enough heat to maintain a liquid ocean beneath the ice, connected to the surface through those fractures. Over the following years, Cassini flew directly through those plumes, analyzing their chemistry. It found water, simple organic compounds, and molecular hydrogen, a strong signal that hydrothermal chemical reactions were happening on the ocean floor, similar to the vents on Earth's seafloor that support entire ecosystems without sunlight. By the time Cassini's mission ended, scientists had confirmed 5 of the 6 chemical elements considered essential for life as we know it: carbon, hydrogen, nitrogen, oxygen, and sulfur, inside Enceladus's ocean. One element was missing: phosphorus. It isn't a minor detail. Phosphorus is a structural backbone of DNA and RNA, and it's essential to how living cells store and transfer energy. Without it, life as we understand it cannot exist. Cassini's instruments simply weren't sensitive enough to detect it during its active mission. In June 2023, 6 years after Cassini's destruction, a research team led by planetary scientist Frank Postberg went back into Cassini's archived data using improved analysis techniques that didn't exist during the mission itself. In ice grains Cassini had collected from Enceladus's plumes years earlier, they found phosphorus, not in trace amounts, but at concentrations far higher than those found in Earth's own oceans. The discovery, published in the journal Nature, completed the full chemical inventory required for life as we understand it. Sitting inside the ocean of a small moon, nobody had reason to study closely before 2005. Here's the detail that makes this story remarkable. Cassini didn't need a new mission to make this discovery. The raw data had been sitting in an archive since the spacecraft's flybys years earlier. Nobody was equipped to detect phosphorus with the tools available at the time. It took better instruments and improved analysis techniques, built years after Cassini stopped transmitting, to finally see what had been there all along. Cassini's mission officially ended in September 2017. Its science did not. Papers on Saturn's ring chemistry are still being published. The magnetic field alignment puzzle is still unsolved. And in 2023, the James Webb Space Telescope confirmed that Enceladus's water vapor plume extends across a region even larger than Cassini had ever mapped, stretching into a vast cloud surrounding the entire E-ring. Almost certainly, there is more waiting inside Cassini's archive, discoveries the spacecraft already made, that no one has been equipped to find yet. On September 15, 2017, at 7:55 a.m. Eastern Time, Cassini's signal disappeared as the spacecraft burned apart in Saturn's atmosphere at 111,000 kilometers per hour. Engineers who had spent years of their careers on the mission watched the signal hold steady until atmospheric drag became too strong for the antenna to stay pointed at Earth, and then it simply stopped. It was, for many of them, the end of a 13-year relationship with a distant world, but nothing about what Cassini found suggests the story is finished. It contains no aliens, no hidden signals, no cover-up. What it contains is something more durable than any single dramatic claim, proof that a planet humans have studied since before the invention of the telescope still holds fundamental secrets we haven't cracked. It contains a moon with an ocean that now satisfies every known chemical requirement for life. It contains a ring system more chemically active than any model predicted, and it contains a magnetic field that challenges the same physics used to explain every other planet in our solar system. Whether life actually exists in Enceladus' ocean remains unknown. No mission has found it yet. But the distance between we don't know if the ingredients are there and we don't know if those ingredients became life is the entire journey this story has taken, from Cassini's first glimpse of the plumes in 2005 to a phosphorus discovery buried in old data and uncovered in 2023. The next mission to Enceladus, one built specifically to search for signs of life in those plumes, has not yet been approved or funded as of 2026. But the case for it rests entirely on what Cassini already found. The ocean is there, the heat is there, the chemistry is there. The only question left is the one no instrument we've sent so far has been able to answer. If you want more real documented science, the kind that doesn't need exaggeration to be extraordinary, subscribe to Infinity Alert and turn on notifications, because the next chapter of this story is still being written.